I'm really delighted this afternoon to be able to introduce one of the MSR AI distinguished lecturers in David Bly, who's from the University of Columbia University. He is a professor in statistics, computer science, and in the Institute for Data Science. David, and before that he was at, Princeton, CMU, and got his PhD with Mike Jordan at Berkeley about 15 years ago. So a youngster by my standards. And he's amazingly famous for his work in topic modeling, both the theory and the practice of it, as well as more generally in Bayesian machine learning. David is, as I said, very well known. He has awards. He's a fellow of the ACM, a fellow of the IMS, the Institute for Mathematical Statistics. He's won the ACM Prize in Computing, and he has several Test of Time awards in both machine learning and information retrieval and other conferences. The breadth of his influence is also seen, I think, in his citations. He's somebody who has almost 70,000 citations, 27,000 of them for one paper that I will mention in passing. That's almost 7 citations per workday since it was published in 2004. And it's the work, which is how I got to know him, on latent Dirichlet allocation. So he took some of the work that I had done earlier and others on latent semantic indexing, work that Thomas Hoffman and Christos Papadimitriou had done on generative models, probabilistic models for word embeddings, and really generalized that on a number of dimensions, put it on sound probabilistic foundations. And as you can see, that paper has had tremendous influence in both statistics and computer science community over the years. His co-authors on that paper were Andrew Ng and Michael Jordan, also very well-known researchers in computer science. He's long had a great relationship with Microsoft Research. I think he, as a graduate student, he was supported by an MSR fellowship. He did an internship here with David Heckerman, and who was your office mate was Hal Daumet. And we've remained close friends with David and his students, through the years. Today, and he's done over the years more than the LDA paper. He's done really foundational work on approximate inference. He's done a lot of work adapting topic models to include structure, hierarchical structure, temporal structure, and really applied these ideas to lots of real-world problems, whether it's looking at 100 years of papers in Science or the New York Times, or looking at electronic medical records. And I think that back and forth between theory and practice, so taking a problem that grabs you and then trying to understand it and improve the models to accommodate it, are one of the measures of his success in my mind. Today, since he's gone to Columbia, he's shifted gears a little bit and has been doing a lot of work on causal reasoning. And today what he's going to do is tell us about some of that work. And the basic idea is to think about how we can do causal inference from observational data when we haven't done nicely controlled experiments. And as the title of the talk suggests, there are some advantages to be found when you have multiple causal variables, and that they have some structural relationship amongst each other. And so he's going to leverage some of that in his talk. So without further ado, I'll bring on David to give us an awesome talk.
Thanks, Sue, for that wonderful introduction. It's great to be here at MSR. Like Sue said, I've been coming here since I was a graduate student. In 2000, I think I came for the first time. And I'm from Columbia, and I'm going to talk about the blessings of multiple causes. So I wanted to start by just telling you a little bit about what my group works on at Columbia. Okay, but I didn't even need to say this. We have complicated data. We want to make sense of it. Okay, well, this is true in many, many settings. It might be that we have a big collection of text documents, like for LSA or LDA, and we want to understand what's in the text documents. Maybe we're econometricians. We have a big data set about people buying food at the supermarket. We want to understand how people shop. Maybe we built a big social network, and we want to understand make sense of people connecting to each other and sending messages to each other, or maybe we're physicists and we want to understand something about the universe from our complicated data about the universe. So let's unpack this statement a little bit. What is complicated data? Well, traditionally that might mean it's just big. We have many, many data points, or it's wide. We have many, many dimensions, many things that we measure about those data points. But data can be complicated, especially the kind of data you look at here, in other ways. Like we might have elaborate structures and relationships, like in text data, where there's syntactic structure and semantic structure. Or we might have data, especially common now, where we have different interconnected types of data, like we might have images, links, texts, clicks, if we have search engine logs, or if we have a big social network or something like that. So these are all ways that data is complicated. It's more complicated than it was when your grandparents were analyzing data. So what does it mean to make sense of data? Well, that also has several meanings. Again, the meaning we might first think of is we want to make predictions about the future. Okay, I ingest the query log for this much time, and I want to know what's the query log going to look like tomorrow. Okay, but there are other ways of making sense of data too. We might want to identify interpretable patterns, what types of queries are being sent. Or we might want to do science, confirm, elaborate, and form causal theories. In other words, I want to understand something about how people search for things based on the query logs. And I see these as almost three different levels of making sense of data. So what we work on in my lab is probabilistic machine learning. This is about developing machine learning methods that connect our domain knowledge and theories about these different domains to the data that we want to analyze within them. And the idea is that probabilistic machine learning is a methodology for articulating assumptions and then for computing with those assumptions. Basically, say what we want to say about how we think the universe is formed and then compute under those assumptions about the data that we see there. And our goal in my lab is to make this way of doing machine learning expressive, so that we can express many different kinds of assumptions about data, scalable, so we can handle the kinds of massive data sets that we encounter today, and easy to develop, so that we can easily program these types of machine learning solutions. Just to be clear, it's not that different from applied Bayesian statistics, which are statistical methods that connect domain knowledge to data. Okay. So some of the work that we've done in my group recently, here's a picture of communities discovered in a big 3.7 million node network, so finding overlapping communities in a big network. This is some analysis of fMRI data, where we had a big data set of fMRI measurements, people looking at different things under the fMRI machine, and we want to know which parts of the brain are active when they're looking at different things. Here's a topic model, like what Sue mentioned. This one's fit to 1.8 million articles from the New York Times. When we were first working on this, we analyzed 5,000 articles. Now we can analyze 1.8 million articles just on a laptop. And here, this is a topic model where each little node here is a collection of words associated under a single theme discovered by the algorithm. This is a population genetics analysis of a big data set of people's genes that tries to capture ancestral structure, which ancestries mix to form the people in the data set. And more recently, we've been working with econometricians. This is a fancy discrete choice analysis, an analysis of how people purchase things, of 5.7 million supermarket purchases. And this picture was a big deal to the economists. It shows us that crackers and cheese go together. Okay, so all those pictures are from recent applied work in our lab. And they all follow, in some sense, this pipeline. I call it the probabilistic pipeline, where we start with our knowledge about the world and a question we want to answer. We use it to make assumptions in the form of a probability model that has hidden and observed variables. We then square our modeling assumptions and our data to discover patterns, to infer the hidden variables given the observations. And finally, we use those discovered patterns to form predictions, to explore, to do whatever it is we're going to do with the data set. And I like this picture. You might think it's a little vacuous, but I like this picture because it separates these activities of articulating our theories and assumptions, computing about them, and then using the results of that computation. And this makes it easy, or easier, to collaborate with domain experts on solving machine learning problems. So what we work on really every aspect of this picture. I have other talks about making assumptions or discovering patterns. But what I want to talk about today is the last box. What do we do with those discovered patterns? And in particular, I want to talk about, as Sue mentioned, how can we understand the world through observational data, right? So causal inference from observational data. This is important. If you sit down with a domain expert and start talking about her data, you learn that what almost everybody wants to do is some kind of causal inference, really understand how the world works from their data. And this is true in any field. And I want to talk about how to use probabilistic machine learning to do this kind of causal inference. I should mention, this is all joint work with my student Yixin Wang. Anything you like about this work is Yixin's contribution. Whatever you don't like about the work was my injected variance to this. So I'm going to start with this idea called the deconfounder. Okay, so we've been talking about lots of important problems, but let's talk about a silly, not important problem, which is the problem of determining how much money an actor is worth. Okay, so imagine you're a big shot movie producer, and you have a bunch of data about movies, who is in the movie and how much money the movie made. And your goal is to understand the causal effect of putting an actor in the movie. Okay? This is causal because it's a question about an intervention. How much money will the movie make if I make a movie with a particular cast? Okay, so here's the data. This is real data. And you can see each row is a movie. There's Avatar, and this is who's in the movie. And then at the last column is how much money the movie made. And the naive solution to solving this problem would be to fit a regression, right? Or even more naively, use deep learning. Okay? And what we would do is when you use deep learning, you just throw the actors in as features, who's in what movie is a feature, and then the revenue is the response, and you build a little neural network that takes in a cast and spits out a response. This estimates the revenue as a function of which actors are cast. Okay, but standard machine learning doesn't provide causal inferences, and if you're new to causal inference, it's all about the tense of the verb that you use. Whether an actor was cast in a movie is different from casting an actor. Right? If you go to the movies and Sue is in the movie, that's different from you saying, I'm going to make a movie and I'm going to put Sue in the movie. Okay? Causal inference is about prediction under intervention. What will the movie make if I put Sue in the movie? What's the problem with causal inference from observational data? It's summarized well by this picture. So I have some bullets about this picture if you don't know it. So this is a picture from the movie From Russia with Love. It's a James Bond movie from the 60s. And as far as causal inference is concerned, here's what you should know about James Bond movies. James Bond movies are about James Bond, a British spy. Okay, this is James Bond here. He's played by Sean Connery, who, by the way, is a very good actor. But James Bond movies, it's a series, and they always cast the same group of characters. Okay, there's James Bond, but there's other people too. There's the person playing M, that's the person in charge of the British Secret Service. There's the person playing Q. He's the guy that gives James Bond his gadgets, like the pen that makes people faint and stuff. And there's also Miss Moneypenny, who's not pictured here. She's M's secretary. Okay, so they're all in all the James Bond movies. And fourth, then I'll go to third, James Bond movies always do well at the box office. They make a lot of money. Whenever you make a James Bond movie, it'll make a lot of money. And also, M, Q, and Miss Moneypenny, they only appear in James Bond movies. Okay, those are the only movies they're in. Sean Connery's in other movies too. And if you know more about James Bond than I hope, then just pretend there's only one James Bond. Okay, pretend that only Sean Connery is James Bond. You might want to pretend that anyway. Okay, so what's the problem with James Bond movies? Well, imagine now running a simple regression on that data, and what you'll see, because M, Q, and Miss Moneypenny are only in James Bond movies, that you're going to learn that they're worth a lot of money, right? If I put whoever plays M in my movie, it's going to make a lot of money because all the movies that M appeared in make a lot of money.
That's not a bad assumption.
What's that?
That's not a bad assumption with the previous M.
She said that's not a bad assumption with the previous M. She knows too much about James Bond movies for this to be a useful education. But that's the idea, right? That a naive regression is going to say that M is worth a lot of money because whenever M is in a movie, it makes a lot of money. But of course, we know that's not true, right? And so in the world of causal inference, the deal is that James Bondness is what's called an unobserved confounder. A confounder is a variable, I've pictured it here, that affects both the causes, who is in the movie, and the effect. And confounders bias passive machine learning when it's used to form a prediction about an intervention. Okay? Some actors are overestimated, like M and Q, and others are underestimated, like Sean Connery. And that's the idea. And unobserved confounders are everywhere. If you want to make causal inferences about all kinds of domains like this, there are going to be some unobserved confounders like James Bondness lurking in your data set. And this is the key challenge to causal inference from observational data. Okay, so what's the classical solution to this problem of unobserved confounders? Well, it's to observe them. So first, you want to do a causal inference. So first, you think about what confounders might be in your data. Okay? That's the first step. Then you measure those confounders. Okay? This is a test tube. Okay? That's somebody measuring confounders. Then you add the confounders to your data set and you estimate the causal effects using the beautiful theory of causal inference. Okay, so this classical approach to causal inference requires that we find and measure all the confounders, a sufficient set of confounders to make causal inference possible. But whether or not we've included a sufficient number of confounders is famously untestable. Okay, and so this classical solution rests on hope and makes us worry. And that's why I drew this person with worried eyebrows, because they're worried that they're missing some confounders. But the point of this talk is that this problem is not classical. Instead of a typical causal inference problem, does Advil help with headaches, we have many possible causes, one per actor. So we call this a multiple causal inference. And the idea behind this work is that when you have multiple causes, they help us construct a variable that contains some of the unobserved confounders. Okay, that's the whole point of this talk, that when we have this type of setting, we can construct a variable that contains some of the unobserved confounders. And in fact, it's a variable that's constructed in all of these types of latent variable models that I showed you in the beginning when I was talking about the work in my group. Okay, so here's the idea. We call it the deconfounder. First, we're going to model the assigned causes. Okay, so here A are the actors, who's in what movie. We're going to build a little probability model of who's in the movie, like a matrix factorization. Then we're going to use that model to estimate what we call a substitute confounder. It's the local latent variable for each movie. And then we're going to use that substitute confounder as though it were a real confounder and correct for it to perform causal inference. Okay, so that's the idea. I'm going to explain it in detail later. Okay, so in words, find, fit, and check a factor model of the assigned causes. Use that model to form a substitute confounder, and then use the substitute confounders downstream in a causal model of the outcome that you care about. Okay, for those of you familiar with these ideas, for example, you might find, fit, and check a probabilistic matrix factorization of movie casts. Okay, so treat the movie cast as a big matrix and factorize that matrix, just the movie casts. Then use that model to infer a per movie variable in the matrix factorization, and then use that per movie variable as though it were an unobserved confounder, now observed, and correct the regression from casts to earnings with it. Okay, and it works. So the value of M and Q go down, and the value of Sean Connery goes up when we do this. Equally superfluously, we can look at who gets better and who gets worse, or who is valued more and who is valued less when we correct for confounding in this movie example. We find that Arnold Schwarzenegger and Robert De Niro and Brad Pitt are overestimated. Their value goes down when we correct for confounding. Antonio Banderas and Cate Blanchett and Nick Cage and Owen Wilson are underestimated. Their value goes up when we correct for confounding. And Christopher Walken and Susan Sarandon and Ben Affleck and Stanley Tucci and Willem Dafoe. I always remember Willem Dafoe because my wife has a crush on Willem Dafoe. They are the most corrected actors. They're the ones that go up the most. Okay, so once I gave this talk and there was like a reporter in the audience, and later she asked me, were those results credible? And they're not. These are not credible results. Okay, but they show you that we get different estimates when we correct for confounding in this way. And I'll show you some real simulations at the end of the talk. So why does this work? The intuition is that multi-cause confounders like James Bondness that affect multiple of the actors as well as the revenue, induce dependencies among the causes appearing in the data, right? So James Bondness induces a dependency between whoever plays M and whoever plays Q. And that dependence is encoded in the data. While we can't observe James Bondness, we can see that M and Q seem to be connected to each other. And so we can capture it with a factor model. The assumption that we make, rather than no unobserved confounders, is that there are no unobserved single cause confounders. In particular, there's no variable lurking in my data that only affects whether Sean Connery's in the movie and the revenue. That would be an unobserved single cause confounder. But what we claim is that no unobserved single cause confounders is weaker than no unobserved confounders. So this is causal inference with weaker assumptions than classically is required. Yeah?
I have just a quick question about the James Bond thing. I can imagine a world where M really was the reason that the James Bond movies were successful, and yet the data is showing that it's Sean Connery who's responsible. So what is it that's making that distinction?
So, right. You're saying you can imagine a world where M only appears in the James Bond movies, but
he's the star.
But he is. You see it for M.
Yep.
Yeah. If that's the case, then but Sean Connery still appears in all the usual movies that he also appears in.
Same observed.
If that were the case, then those movies wouldn't do as well. The other Sean Connery movies. Yeah.
But then you have like Miss Penny or whatever.
Miss Moneypenny?
Yeah, and they kind of, just also get the benefit of being alongside M, who's actually driving the revenue.
Yeah, so first, then Sean Connery's movies wouldn't make as much money if that were the case. But to be clear, let's say M is really the star, but M only ever appears with Q and Miss Moneypenny. This method cannot tell the difference. No method could tell the difference between M being the star or Q being the star or Miss Moneypenny being the star because they are perfectly dependent. Yeah.
How do you measure time? A lot of the times profits, an effect of a movie is not measurable instantaneously. So I'm going to say a movie that was released 10 years ago, this is how much money it made. The movie was released yesterday, didn't make as much money. Is that a fair comparison?
Right. So I think this is revenue after so many months, and it's somehow corrected for the change in time. Yashin, I believe, did that to the response. Had she not, it's my fault. Okay. Now, the actor example, of course, is not the only multiple causal inference. This is kind of everywhere. So how do genes affect a trait? The causes are genetic variation, which we might measure, on 100,000 locations in the genome. The effect is the trait itself. And the confounder is ancestry. Each person's ancestry induces a correlation in multiple genes, just like James Bondness induces a correlation among multiple actors. And this can confound our estimate of the effect of each gene on the trait. Okay, in sports, the causes might be who is in the game. The effect is the points scored in the game. You want to know the value of a player. But the confounder is that the coach might use multiple players together. In economics, the causes might be the prices of each item for sale. That's what you're interested in, the causal effect of the price of peanut butter. The effect is how much money is spent by consumers. If I raise the price of peanut butter, how's that going to change the economy? And the confounder are things like holidays and seasonality, which affect the prices and demand for multiple items. Okay, so these unobserved confounders, but multiple causal inference problems are all over the place. Okay, so that's the idea. Here are some of the details. So our observed data set, D, is a collection A1Y1 to ANYN. Each A is a collection of causes. So here it's like a bunch of binary variables for whether or not which actor is in this movie, the I movie. The outcome is YI. And our goal is, again, to do causal inference, to look at the expectation of the revenue, and this is the Pearl's do notation in the world where I intervene and I set the cast equal to A. Okay, or I might look for some contrast of, here's a cast and I change the cast by one person, for example. Okay, so you read this as the expectation of Y in the model where I intervene on A. Now, the problem of causal inference is that if there are unobserved confounders, then the interventional expectation does not equal the conditional expectation. The conditional expectation I can get from my data, but the interventional expectation is not the thing I can get from my data. Okay, again, we're going to find, fit, and check a factor model of movie casts, use it to form substitute confounders, and then use those substitute confounders downstream in a causal model. So let's go through each of those steps. When I say probabilistic factor model, I mean a model that has the following form. For each cause, there's some representation, beta j, that comes from a prior. For each individual, each movie, for example, there is some representation zi that comes from a prior. And then, whether or not actor J is in movie I comes from some distribution that depends on the movie representation and the actor representation. Okay, this is what we mean by a factor model. And it turns out if you squint at a lot of the models that you might learn about in a machine learning course, mixture models, matrix factorization, deep generative models, topic models, etc., models that you would find by opening these books to a random page, they are factor models. Okay, so you can kind of look at all of these things as types of factor models in this sense. Okay, so here's a factor model I like. It's called Poisson Factorization, just as an example. And what it says as a generative model is that there's a k vector of non-negative values beta for each actor. There's a k vector of non-negative values z for each movie. And then whether or not actor I appears in movie J comes from a Poisson or a truncated Poisson whose rate is the inner product of those two representations. Okay, this is like a Bayesian version of non-negative matrix factorization, okay, and called Poisson Factorization. It's a nice model because it provides a generative model of these assigned causes, and it can be fit to large data sets with variational methods. Okay, so in the first step, what we do is we fit one of these factor models to just the assigned causes. Okay, so to be clear, we throw away the outcome in this step. Consider the data set of casts, approximate the posterior distribution of the per movie representation and the per actor representation using something like variational inference or whatever you want. And that's the first step of the deconfounder. Again, we only model the actors. The outcome is not involved. Okay, so here's an example. Here are different movies. Well, here are different movies, and here's an example of the per movie representation that we get in this way. Okay, and we're not going to try to interpret it. They sort of are interpretable, but the point is that we get this per movie representation. Okay, so in the second step of the deconfounder, what we're going to do is estimate the local latent variable, zi. And zi hat is going to be the posterior expectation of the ith movie's representation given its cast and our representation of the actors. Okay, and that's what we've illustrated here. These are some zi hats for different movies. We're then going to check how well zi hat captures the distribution of actors. Okay, how well does the representation of Unforgiven capture the actual cast of Unforgiven? And I don't have details in this talk, but there are some extra slides at the end. We can use some kind of predictive check on actors, or you could just take held out data or whatever you want to check the fidelity of zi hat. Okay, so those are the first two steps. Fit one of these factor models, and then estimate the local latent variable and see how well it captures your distribution of data. Now, to be clear, I use Poisson Factorization just as an example, but you can use any factor model. Okay, so probabilistic PCA, Poisson Factorization, mixture models, deep exponential families, these are all examples of probabilistic factor models, and each one performs differently in terms of measuring how well it captures the distribution of actors. Okay, and you make a little table like this to decide which factor model fits best. Yeah?
Can you explain what you mean by captures? So you're using Z to predict B?
Yeah, no, I'm using Z to predict A. I'm using Z to predict who is in the movie.
Okay.
Yep. So just to make it really clear, take your casts, fit the model. Say take your casts for each movie, hold out 2 or 3 actors. Yeah. Fit your model to the remaining actors, and then ask how well did the fitted model capture the held out actors. That's a check of how well I'm capturing the population distribution of actors using my fitted Zs. Yeah. Okay, and so this predictive check produces a predictive score. It's all very mysterious on this slide. But the point of this is that, look, these three models loosely passed the check, but this mixture model failed. The mixture model was not expressive enough to capture the distribution of actors. Now, the idea is that the estimated local variables, if they pass that check, are substitute confounders. They are the latent attributes of movie casts, and they capture these multi-cause confounders that we talked about in the first part of the talk. So the next step is to form an augmented data set where I have the cast, the revenue, and this Z hat. Notice I didn't go and measure anything like James Bondness or sequels or whatever it is that I think might be confounding my estimates. Rather, I just used Z hat, which passed some kind of predictive check. Okay, so now here's my augmented data set with the Z hats next to the casts, next to the revenue. And then finally, I'm going to use the substitute confounder in a causal inference. For example, what that means is that I'm going to fit some kind of model of my revenue given the cast and my substitute confounder. Okay, this is the simplest one. It's just a regression. It doesn't work the best, where it just says there's a coefficient for the cast and a coefficient for the substitute confounder, and I fit this regression to this data. Finally, this is the only part I won't explain, use some kind of causal inference then to use the results of that regression to estimate the interventional expectation. Okay, so this, for example, is called the G formula, and loosely it is how to correct for confounding if you had observed the confounders. Okay, it's looking at a weighted average of expected revenues given substitute confounders and casts. Okay, so those are the three steps. Find, fit, and check a factor model of movie casts, use it to form substitute confounders, and then use the substitute confounder downstream in a causal inference. And the steps, from the modeling perspective, are choosing a factor model and choosing what we call an outcome model, a way to capture revenue given substitute confounding and cast.
How do you tell how many substitute confounders?
Good question. So how do we choose the cardinality of Z? I have an answer, and then I really don't know the answer. What we do is we choose K, the cardinality of Z, to be big enough to pass the predictive check, but no bigger. And the reason is that if it's bigger, then it's going to start capturing stuff about the actors that we need to estimate the downstream causal effects. And this has to do with like the bias variance trade-off of this procedure, which we don't totally understand.
You don't want to overfit.
Right. If you here overfitting has bad consequences, because if you overfit, you lose a lot of the information that you need to estimate the downstream causal effects. Okay, this is how I got this credible picture. Okay, so.
Quick question.
Yeah, please.
What is the role of beta in the model? Is it just marginalized out when you...
We just take a point estimate of beta. We look at the Bayes estimate, the expectation of beta given the data. You can do whatever you want with beta. What's really important is Z. So you need beta to help define how Z defines a distribution of actors, but it can be a point estimate or it can be a whatever you want. Yeah. Okay, so I've kind of asserted for you twice that this algorithm is a good algorithm, and the paper tells you why it works, but I want to kind of give you a hint at what the theory is around this procedure. Okay, and so the theory says the following. Suppose we fit a good factor model of the assigned causes. And by good, I mean one that captures the distribution of actors. Then its local latent variable, Z, will capture multi-cause confounders. The main assumption is that there are no single cause confounders. And stopping short of a full proof, there's a graphical model argument that basically gives you all the intuition about why this is true. Okay, so here's a little graphical model. And here I have the variables AI1 to AIM, for each actor, whether or not he or she is in the movie. Now, if I find a good factor model, then that means that the joint distribution of the actors is described by this picture. And in this picture, because you know about graphical models, because they were practically invented here, the conditional distribution, the joint distribution of the actors are conditionally independent given the substitute confounder and beta. Right? That's what this picture tells us. Beta is lurking in the background here. Just focus on the substitute confounder. If their joint is described by this picture, then they are conditionally independent given the latent variable. Now, let's add the outcome. Here's the outcome yi. Here is a multi-cause confounder, W. Okay? Now, why is it a multi-cause confounder? Well, it is correlated to the outcome, and it's also correlated to several causes. The theory says that W cannot exist if we have described the joint distribution with this latent variable model, because if W did exist, then AI1 to AIM would not be conditionally independent given Z. And you can see that just by looking at this backdoor path from A to W, right? Even if I condition on Z, AI1 is going to be dependent on AIM here. Make sense? And so that's a contradiction, so W can't exist. There can't be, whatever information is in W that we're assuming is there, that information is also going to be in Z. And this is all made more formal in the paper. Now, as for the assumption that there's no single cause confounder, well, you can see that that does not break this conditional independence assumption, right? If SI is lurking in the background and it affects whether Sean Connery's in the movie and the revenue, SI can still exist because the fact that SI is there does not break the conditional independence that given Z, these A's are independent. Okay, so the theorem is that if the population distribution of causes can be written as a factor model, then the local latent variable blocks the backdoor path between the causes and the effect, which means we can use it to correct for confounding. This implies that I can write down the interventional expectation using backdoor adjustment. It's a little more complicated than this, but if you're interested in how it's more complicated, ask me at the end, and I have some slides at the end about how it's a little bit more complicated. Yeah?
So intuitively then, if I have a multi-cause confounder where the number of things it's actually affecting is becoming larger and larger, does my data requirement actually become worse because I have to intuitively estimate like higher moments of the data?
Sorry, if you have a multi-cause confounder,
so
that affects more and more causes.
Yeah, so suppose I had something that only affects like 2 actors versus something that always jointly affects like a couple of hundred actors.
Yep.
How does my data requirement change?
I don't know how to think about that. And I'll tell you why. On the one hand, if I have a multi-cause confounder that only affects a couple of the causes, then in the causal inference part of my algorithm, it's not adding too much confounding. There probably won't be that much confounding bias due to that multi-cause confounder. So that should make me feel good about a multi-cause confounder that only affects a couple. However, that multi-cause confounder is going to be harder to capture with the factor model. Whereas a multi-cause confounder like you described that affects many, many, many actors, let's say James Bond movies contain thousands of people in them, then that one's going to be easy to capture from the data. So these are at odds with each other. Yeah, it's an interesting question. Okay, so that's a little bit about why it works. We ran many simulations and studies. Okay, here's a collage that I made of the simulations and studies that we ran. Good. Good. Let it have its effect on you. Okay, so one of the simulations is around GWAS. So GWAS, genome-wide association studies, is a problem of multiple causal inference. And the question we want to answer there is, how is genetic variation causally connected to a trait? And the problem, and so in GWAS, for every individual, we measure a trait, like their height, and then many, many measurements of their genome, SNPs, single nucleotide polymorphisms. Now, in GWAS studies, multiple cause confounding is a problem non-causal SNPs, non-causal variation, could be highly correlated to causal variation because of latent ancestry, and this misestimates causal effects, right? M is overestimated and Sean Connery is underestimated. So we ran a simulation. Here's our data. First, we generate genetic variation where each individual belongs to some latent group CI, some latent ancestral group. Okay, and so we made 100,000 SNPs for each person, and their values are 1, 0, or 2. And we generated this from some kind of realistic model of genetic variation that included this latent ancestry. Then we modeled the outcome, like height, and we modeled it from a little regression where each SNP has some coefficient, beta j. The beta j's are sparse, so only some of the SNPs are causal. Then there's an intercept term that uses the latent ancestry. And then there is a noise term, and the noise term also depends on the latent ancestry in terms of its variance. Okay? So notice that the latent ancestry, or the observed ancestry in the simulation, is a confounder, right? It affects both the SNPs and the outcome that we care about. Okay, so there's confounding here built into this data. Now, we're going to do the deconfounder thing. We fit many factor models, and I want to emphasize that none of them is the true model. Okay, so none of them is the model that generated the SNPs, but they're all factor models, probabilistic factor models, and each of them performs differently in terms of how well they capture the population distribution of the causes. Okay? It's not what this talk is about, but I should add that we did all of this with a probabilistic programming system. Okay, so when you want to fit many, many probability models, it's not just that we're going to run one model and then write a paper about it, but we're going to fit many models. We use probabilistic programming to help us do inference easily on many models. Okay, so we fit many factor models. Then we fit outcome models with no control, so ignoring that there might be confounders. Controlling for the confounders, where we magically observe the confounders that we don't really get to observe, and then using each of these factor models to form a substitute confounder. Okay, I also want to emphasize each of these as a factor model has some notion of a local variable, but they're all different, right? So the deep exponential family, for example, is like a deep learning type model. It's got a multi-layered local latent variable. Poisson Factorization has a non-negative local latent variable. Probabilistic PCA has a real valued local latent variable. But the idea behind the method is that each of those local variables could potentially capture the unobserved confounding. Okay, and so we used each of them to give us a substitute confounder. And here we see the mean squared error between our estimates of the coefficients beta and the truth for the causal SNPs. And what you can see is the following story. If we don't control for confounding, we're far away from the truth. If we control for confounding, we're quite a bit closer. But these deconfounded estimates also get closer, even though we don't get to observe the confounding. And moreover, when the predictive check fails, the estimate of the causal coefficient also fails. And when the predictive check did best, the estimate of the causal coefficient also did best. Okay, so this is suggesting that the method works well. In fact, in the world of genome-wide association studies, this technique of reducing the dimension of the SNPs and then using that reduced dimension to correct for downstream modeling of the outcome is done all the time, although the perspective that what's really happening is that it's capturing unobserved confounding because of this kind of theory is not there, and the idea of predictive checks to understand which confounders are best. So one could take any of these methods, you could square them off against each other, which is essentially what we did here, to understand which ones work best with GWAS data. Okay, so that's my talk. How can we understand the world through observation? It's important everywhere, and I showed you how to use probabilistic machine learning to help do causal inference from observational data. Again, find, fit, and check the factor model of assigned causes, use it to form substitute confounders for each individual, and then use those substitute confounders downstream in a causal model. If we find a good factor model of the assigned causes, then its local latent variable will contain multi-cause confounders. That's our theorem, but of course, there are assumptions. This uses probabilistic machine learning. I didn't mention this, but this doesn't require any kind of exact inference. Okay, so Poisson factorization, we can't do exact inference, but that doesn't matter because all we're doing is checking that those z's capture the distribution of the other causes. And this requires weaker assumptions than classical causal inference. Okay, so if you're interested in reading more, there's our paper. There's some other readings about multiple causality, and we're doing a lot of current research on multiple causality, including a lot of applications to some things that you care about here, like medicine, recommendation systems, and fairness. Thanks very much. Yeah.
So you mentioned like the number of those confounders. That's one factor about like you want to balance the bias and trade-off. But it seems like there is another dimension, which is like whether you're making some sort of linear combination versus a non-linear, like the different.
Yeah. So yeah, I'll repeat the question. So the question was, I talked about the bias variance trade-off around the number of latent factors in the factor model. But you're saying that there's also another decision to make about the outcome model. Is it linear, is it nonlinear? And that's true. So the outcome model that works best for us really is a nonlinear one. It's one where it's a linear, but it's linear in a nonlinear function of the substitute confounder, where you form what we call the reconstructed causes. These are the A hat. It's the expectation of A given Z hat. It's the cast you think you would get if Z hat were the substitute confounder. And when A hat is brought into the outcome model, say a regression, we only tried regressions, then that's a nonlinear function, but that performs much better than this linear model taking Z hat directly. But again, understanding the bias variance trade-off is something that's on our list. Like with what you suggest, that would incur even more variance, but might be more accurate. Yeah. Yeah.
My question is about the fairness application of this kind of an approach, in the sense that imagine there's a minority class that are historical other kind of reasons, and that's, I think, a confounding factor that could be explained by such a model. Explaining it doesn't really change the fact that the recommendation engine may never recommend somebody from that minority population, because there's no positive evidence to show that those people could succeed at a given job because they were never given that opportunity.
Yeah.
What are your thoughts about these kind of approaches and the intervention, and whether they are satisfactory to have the right intervention?
That's a good question. So, our work in fairness is, so there's kind of, the reason it connects to the deconfounder is the following. Our work in fairness is around setting up a causal model of the attributes, both the sensitive and non-sensitive attributes, including things like a sensitive attribute having an effect on a non-sensitive attribute because of some kind of unfair situation in society. And then using that model to then form machine learning predictors that can satisfy various causal metrics for fairness. Okay, so that's our work in fairness. But ours and other work in fairness often presupposes that you have a good causal model, an unconfounded causal model. And so here we can use this with those kinds of data sets to produce a deconfounded causal model of these sensitive and non-sensitive attributes, and then use them downstream in some way to correct for example, for the disparate effect that using a test to do admissions, for example, might have on a protected group. That said, you brought up an interesting situation where there's zero overlap, where if there really was a situation where nobody was ever, so the methods that we develop would do things like upweight the information when someone who was unlikely to get in got in and then did well, for example. But when there's no overlap, I don't think there is a mathematical solution to that. Yeah.
So what do you think about applying particle pipeline to the more naive methods like VAEs, where you maybe like substitute the encoder part with the part that creates those substitute confounders?
Yeah, so no, a VAE fits the bill. So in a VAE, conditional on, you can set up a VAE, you can set up one of these factor models using a deep generative model, which is the model that the VAE fits. And then as for the second part of the VAE, which is the amortized inference, that is fair game as well. So you could use amortized inference anywhere here as long as the resulting z hats capture the population distribution of the assigned causes.
Yeah, you probably don't have like KL collapse and anything like that if you.
Well, again, the KL collapse, that's a matter of whether or not the inference procedure is working or not. That's separate. So we're using whatever inference procedure we're deciding to use. Of course, if you decide to fit a model where it doesn't fit the data well and the z-hats don't predict the held out causes, be it for KL collapse or another reason, then it won't work.
Okay.
But you'll be able to detect it.
Right, yeah.
Yeah.
If there's a known confounder, is there a relatively straightforward way to eliminate it before you do the factorization so that you don't bother spending effort finding it?
That's a good question. So with known confounders, you can add them anywhere you want. So you can condition on them when you fit Z, or you can not condition on them when you fit Z and only condition on them when you fit the outcome. Right? If there are known single cause confounders or other known confounders, why hope that Z is capturing them when I can condition on it since I've measured it? That said, that does lead to higher variance. So, because you're fitting a higher dimensional model in the outcome model. But yeah, no, so adding known confounders is straightforward. I'm going to think of a way to answer the questions geographically. Okay. And then let me know if you are not if you get a new question. Yes.
So you talked about scalability, but I'm actually kind of interested in the opposite direction, where I can imagine there are a lot of domains, especially in certain science fields, where you might measure, or your data might be very high dimensional, but you might be able to take a couple thousand or even a couple hundred measurements at most. Do you have a sense of how well this is able to capture confounds in that situation?
That's a good question. So, right. Well, in the collage of simulations, there are some low data simulations there, like including with just 2 causes and small data sets. But there's another, I want to mention something else that your question reminds me of. There are a lot of settings where, it might be difficult to obtain data about X and Y, but just data about X is easy to obtain. Then you can use the data about, A and Y, but just data about A is easy to obtain. Then you can use these factor models to with your massive data set of, say, text, to get substitute confounders. And for your smaller data set of text and whatever outcome it is you care about, you can use those substitute confounders, which will be well estimated because they were estimated from the much larger data set, to try to provide an answer to that smaller, more expensive causal inference problem. I'm going this way and then back this way.
Can you briefly discuss some of the theoretical issues with
Oh, yeah, sure. So, I can't do it briefly, but I can do it. Okay, so we wrote this paper, we put it on the archive, and then Alex Dunmore wrote a very nice paper which said that our paper was impossible. So I want to tell you, and so that led us to then refine our theorems a bit to make them possible. And well, let me explain. So in causal inference, if you're not analyzing data, you're worrying about identifiability. And a causal quantity is identifiable if it can be written as a function of the observed variables. In other words, if I observed an infinite amount of data from my process, can I identify some kind of, can I make a prediction under intervention? Can I use the joint distribution of the observable joint distribution to make a prediction about some other joint distribution where I've intervened? That's what identification is about. Now, Alex Dunmore wrote this very nice paper where he gives 2 examples in the multiple causal inference setting where the expectation of Y in the world where I intervene on A is not identifiable. In other words, if, and the 2 settings are one where all the causes are binary and the outcome is binary and the latent confounder is binary, and the other one is the real valued analog. Everything is real, the outcome is real, and the latent confounder is real. And he's right. So the expectation of Y given to A is not identifiable, meaning I can change something about the way the world works and the observation distribution stays the same. Okay, these are nice results. They help flesh out the theory of multiple causal inference, but identification still is possible. So first of all, in the movie example, identification is fine because the causes were binary and the revenue was continuous. But moreover, if you assume that you can pinpoint a substitute confounder, Z hat, then you can identify things like the contrast between two interventions, even in the two settings that Alex Dunmore points out. And also you can identify a subset of causes under intervention, okay, with some other assumptions, but that's the sense in which the theory is a little more nuanced than I gave earlier. Other questions? Yeah.
So it seems like we get a full distribution over Z at the first step when we are fitting these factor models. Why discard all the distribution information and just go after an imputed mean estimate Z when I'm computing these substitute confounders? Like, what am I giving up in that simplification?
Good question. So the question was, I'll repeat the question. It seems like we get a nice distribution over Z, a posterior distribution over Z, and I'll just add to your question, it's a meaningful posterior over Z because that's at the individual level, right? There's only so many actors. That posterior is really going to have some spread to it, as opposed to like a posterior condition on all the data. So why did we then just use the posterior expectation? Okay, so the first answer is for convenience. It was a way to construct an estimate of Z, because what we're getting, there's two distributions of Z at play. There's the posterior that you're mentioning, but then there's also the population distribution of Z, which is like the Z hats across all the movies. Okay, and that's the distribution of Z that we really care about. That's the one that we correct for when we do downstream causal inference. As to your question, we did it for convenience. That said, if you look in the paper at that collage or the simulations that make up the collage, we can use that posterior to do a kind of uncertainty estimation about the causal effect. In particular, rather than use the posterior mean, you could just sample a Z from the posterior and get a collection of samples for each individual, do causal inference, and get a causal effect. Now do the same thing. Get a causal effect. Do the same thing. Get a causal effect. And that gives you a distribution over the causal effect, and that lets you measure the uncertainty of the causal effect. It also, by the way, helps you identify when you're in one of these Dunmore models that's not identified, because then you're going to get this improper distribution as the causal effect. So you can almost identify when you are not identified. Nothing here? Yeah.
So at the beginning you mentioned that in the classical approach it's not testable whether you've gotten a sufficient set of confounders. And
correct.
So I'm wondering here, and maybe the answer to the previous question is relevant, is there some kind of statistical test that you can use to say when your predictive check has been good enough that you can have a certain level of confidence in the outcome?
Good question. So the question is, I'll repeat it again, I said that classically, you just hope that you've thought of all the confounders and that everything's okay, but here, is there some kind of test? And so, right, the predictive check is that test here. Now, the predictive check is, in some sense, heuristic. We have this predictive score that we are thresholding at a particular value to say that the distribution is good enough. We could think about how to make that more rigorous. To be fair, I don't think that's totally our fault, because the whole world of Bayesian model diagnosis is itself not that rigorous. But working on that is something that's on our list to do for sure. That said, the predictive check itself goes beyond just hope and worry, because at least there is a score. Like, I can see the mixture model failing there, for instance. But yeah, no, if the predictive check passes, and of course you have finite data and you have this predictive check, but if it passes and it is capturing the distribution well, then you are safe. You have captured the unobserved multi-cause confounders. The single cause confounders, that's uncheckable. There you need to hope and worry or measure confounders.
So right now we don't know of an explicit connection between the value of that predictive score and differences in the outcome.
Correct. Yeah, that would be a problem to work on. Yep. And it's in the broader field of how do I check a model. So I know that if I have my P of A, the true distribution of A, and then I have my P of A given by the marginal distribution of A via the model, I want to know that those are equal. Yeah. And then, and this is an interesting problem. Kind of a Bayesian model diagnostics and checking is part of the neglected landscape of Bayesian meets frequentist methods, which is worth working on.
Let me take a couple more questions.
Okay, since I did it geographically, I feel like it's unfulfilling. Okay, let's go. Sure, some short questions, I hope.
How practical is the single cause assumption?
Well, that depends on the domain. So, like in genomics, I think it's probably fair. I don't know. I don't know much about genomics. Yeah.
I wasn't sure if it was answered 2 questions ago, but I guess I was thinking about it in the context of, I don't know if it's a dumb question, but especially in the context of the fairness question that was also answered. Could you say, so given your Z, a way to sort of interpret what these confounders are, could you take sort of like a testing approach? So I measure something that I suspect could be a confounder, and then check it against your list of confounders somehow.
Right. So, well, first of all, the types of models that we could fit, like topic models and Poisson Factorization, they're often very interpretable. Like if you looked at these factors that you get out of the Poisson Factorization on movie casts, you see things like the superhero movies come together, right? Because they have this big, maybe that would be a better picture for the youth of today. They have the same cast of characters, Iron Man and the others. That said, I also want to emphasize that it doesn't matter. Now, that's kind of the point. The point is that I don't need to know what kind of crazy confounder goes into choosing movie casts, because all I need to know is that I've captured the population distribution of casts, and then I can answer the question I care about, which is how much is Robert De Niro worth? Yeah.
So we talked about multiple confounders, multiple cause confounders, and single cause confounders. Should we be concerned with zero cause confounders that only affect the outcome but not the predictors?
No, that's a good question, and the answer is no. We don't need to worry about that. So that is, that is just wrapped up in my model of Y. That's adding just variance in my model of Y. Now I could, if I think it helps with estimating accurately the outcome, given the causes and the substitute confounders, sure, I can include it as from like a bias variance perspective, but that doesn't. We don't need to worry about that from the perspective of biasing our causal inferences. With infinite data, that can be ignored. Good question. Oh.
Max was.
These okay.
Finish up your geography.
These two. Okay, this and then Max.
So if I care about a single cause or a very small number of causes, but I want to get more benefit out of your model, can I add extra causes, things that I don't care about, things that maybe don't even affect the outcome that I'm interested in, but might be associated some other way?
Yeah.
What's the limit of like the data I can dump onto the system and the trade-offs?
Good question. So of course you can, right? So these multi-cause confounders are inducing dependencies among things that don't affect the causes, and there's really a deep connection between this work and things like proxy variables and null proxies. And if you look at, we have a follow-up paper about the structural equation model approach to this, which relates to those ideas. But the answer is yes. That those are null proxies. If you have other variables that don't affect the outcome, but are somehow correlated with the causes, those are called null proxies of the confounder, and those do help, or they can help. I guess subject to the bias variance issues as usual. Yeah, thanks, Emily.
If my decision to act in a movie depends on whether you act in the movie, because either we get along or we don't get along, does that make the factorization not work? We get like a bad fit?
So it affects how much residual variance there is in whether you and I are in the movie for understanding how much we're worth. Like if 99% of the time you bring me along to the set to act, then there's only that kind of a little bit of variance left to understand our separate effects. And so that's the issue with that. You could theoretically capture it with the Z, right? You'd capture that dependence, but it would leave little power for estimating the causal effect. That said, something we're working on now are latent mediators. The idea that maybe you're terrible and I'm terrible, but when we're in the movie together, like it's magic. Then the latent mediator could capture that. Yeah.
Okay. Let's wrap up the formal questions. David will be here for the rest of the afternoon.
Yep.
And stop by to chat with you. Thanks.
All right, thanks.